this is going to be a more in-depth understanding of heterogeneous catalysis, meaning that the catalyst is in a different phase from the reactants. The important thing to consider is the surface coverage. So what actually happens in catalysis, it depends on the adsorption, not absorption. The adsorption is when it sticks to the surface. So let's talk about surface energies. If we've got something here stuck to it, that's going to be a different energy to be stuck here. So it's important to note with catalysis is, it's all about the surface, how many layers there are. Is it more thermodynamically or kinetically favourable to be at a certain point, here or here? What actually happens at the surface? For example, say this gets cut in half, let's say this is a plus and a plus. Is that going to have a different surface energy than cutting through these? It's all things that need to be considered. So let's talk more about the general, we can say, mechanism for catalysis. So consider a metal, and this can be anything of your dreams. Carbon monoxide, CO2. So we're just going for a general internal combustion engine catalysis of, like a car, some sort of matrix in your car that converts carbon monoxide into CO2. That comes in, it gets stuck on the metal, and then it leaves. So this is the adsorbent, and this will be desorbed. Yeah, so desorption. So let's call that A, and let's call that D. So if we draw like a general equation, this adsorption can be considered like this. So you've got A, let's make sure this is filming, A, and you have your gas, and let's call the metal M, right? This is going to give you, what's it going to give you? The adsorption. So A adsorbed to the surface. This is the adsorption, right? And you have the desorption. That's just it's going to be the opposite in a way, because it's going to give the gas off again. It's not the same gas, but it's just that we said A is the absorbent, right? It gives us CO2 this time. Now we need to think about equations. So the rate equation, remember the general formula for a rate equation, because it's probably a long time since you did A level, you might not even have done A level. So rate equals K, just something like this. K relates to it. These options. So if we talk about the rate equation of A, so A for adsorption, the rate is going to equal minus D, so the gas, which is going to equal, we need the constant for the specific thing, the adsorption, so Ka of 1 minus theta Pa. Pa, you've seen that before, partial pressure. That's just the amount of pressure that the gas has for it to stick to the surface. Because if there's a lot of pressure, it's going to stick more easily, isn't it? Think about it, it's going to be forced. This theta value, this is the surface coverage. We spoke about this is not a perfectly clean surface in reality, maybe in our minds. So the surface coverage is 1 minus the coverage that's already on the system, because it's poisoned, if you will. There's already things on it. So that's the adsorption. Now let's do desorption. So this is going to equal minus D desorption. Oh no, it's going to be the adsorbent. So ADS. Excuse that beautifulness. And this is going to equal KD for desorption, and just the theta because surface coverage, because once it's stuck on, the only thing that's determining it leaving is how much of it's covered. And because chemists hate calculus, well, I don't mind it, but the general consensus is chemistry, people don't like maths. So if we equate these together, we're not going to integrate or anything, we're just going to set these equal to each other. Forget the rate equations. So you can just say Ka, 1 minus the surface coverage partial pressure. So the adsorption equals the desorption, so Kd theta. We divide by Kd, so we get Ka over Kd. let's do that again, Ka over Kd, that equals 1 minus theta Pa theta. Ka over Kd, this is some constant. So we can just call that alpha, for example. So now we have alpha 1 surface coverage equals that. Now what we're going to do, we're going to divide by 1 minus the surface coverage. This is going to give you the Langmuir isotherm that is spoke about, well, quite briefly. And then we don't want to do, like partial fractions, so I think we can just flip it. So you get 1 over alpha Pa equals 1 theta over theta. So we can see we're getting somewhere now. And then we're just going to finish this off up here. This is going to equal, so 1 over that's just 1 over that. And that equals, theta over theta is minus 1. You whack it on that side. Pa plus 1. So you think about this is y, and you've got your mx plus c. Excuse the formula. Right, that's that.